Hello students, in this lecture we are going to discuss radiation. Then we will see different definitions related to radiations, which are irradiation, radiosity, absorptivity, reflectivity, transmissivity. Then we will discuss emissive power and emissivity. And in the last we will discuss Stefan Boltzmann law and Stefan Boltzmann constant. Okay, so in case of conduction, we have discussed that conduction is the transfer of heat due to actual contacts of molecule, and in the conduction the heat will be transferred from particle to particle which are in direct contact, and conduction is possible only in case of solid. So in this rod we can see that if you supply heat to this end of the rod, the heat will be transmitted through this rod. In case of convection, the heat will transfer due to actual motion of molecule. So if you hold your hand over the heat, in that case the heat will be transferred through this air, and this is convection mode of heat transfer. Whereas in case of radiation, the heat will not be transferred through some medium like this air or the solid. In case of radiation, the heat will be transferred due to electromagnetic waves which are coming out of this fire. Okay, so if we try to define this radiation, the radiation is the transfer of heat due to electromagnetic radiation in wavelength band of 0.1 micron to 100 micron. Okay, so example of this radiation is energy of sun coming to the earth's surface in the form of radiation. So radiation heat transfer does not require any medium as in case of conduction and convection. So we have seen that in conduction we required some solid medium. In case of convection, we require liquid or gas medium, but the radiation can occur without any medium. Okay, so here we have mentioned wavelength band of 0.1 micron to 100 micron. This is because if wavelength is very short or wavelength is very long, then heat transfer is negligible, and in this range, heat transfer is considerable. So here we will discuss the concept of wavelength. The wavelength is the distance between two successive crusts or two successive troughs. Okay, this wavelength can be in kilometers, meters, centimeters, millimeters, micrometers or nanometers. And just we have discussed in the wavelength band of 0.1 micron to 100 micron, the heat transfer is considerable. Okay, so if wavelength is very short, for example, if wavelength is in microns or nanometers, then we will call that wavelength as a short wavelength. And if wavelength is in meters or kilometers, so in that case we will call that wavelength as a longer wavelength. So here we can see radiation spectrum. The radiations which are in the band of 10 to the power minus 13 to 10 to the power minus 11 meters, those are known as gamma rays, and in between 1 nanometer to 10 to the power minus 11 nanometers, those are X-rays, and 0.1 micron to 10 microns, those are known as ultraviolet rays. Then 10 micron to 1 mm are known as microwave and infrared rays, and the wavelength which are above 1 mm, those are known as radio waves. Okay, so you can see applications of various wavelengths in this image. Okay, so now we'll start discussing various definitions regarding this radiation. So first definition is irradiation. So irradiation is denoted by G, and irradiation of a surface is defined as the total radiant energy received per unit time, per unit area from all directions at all wavelengths. So if you consider any surface area, so the radiations coming over that surface area from all directions at all wavelengths are known as irradiation. The next definition is radiosity. It is denoted by J. So radiosity is defined as the total radiant energy leaving a surface area per unit area per unit time. So to summarize, the radiations which are coming on the surface are known as irradiation, and the energy which is leaving the surface is known as radiosity. Okay, and both these things are denoted, and both these radiosity and irradiations are given by watt per meter square. Okay, next definition is absorptivity. Absorptivity is denoted by alpha. It is defined as the fraction of total irradiation absorbed by surface. It is denoted by alpha. Okay, so now if we consider one surface area like this, so the radiation which are coming on this surface are known as irradiation that we just now discussed. Okay, so these irradiations or incident radiations when fall on a surface, at that time three things are possible. So first, these radiations can be absorbed by the surface, or secondly the radiations can be reflected by the surface, or these radiations can be transmitted through the surface. Okay, so what is absorptivity? Absorptivity is the ratio of absorbed irradiation divided by incident radiation. Okay, so for example, if total radiations which are falling on the surface are 100 watt per meter square, and if 70 watt per meter square radiations are absorbed by the surface, then absorptivity will be is equal to 70 divided by 100, that is 0.7. Okay, so value of this alpha should be always in between 0 to 1. Next definition is reflectivity. So we have discussed that when irradiation fall on a surface, at that time those radiations can be absorbed, transmit, or this can be reflected. Okay, so the radiations which are reflected divided by total radiations falling on a surface is known as reflectivity, and this reflectivity is denoted by rho. Okay, so rho is equal to reflected irradiation divided by incident radiation. And again value of this rho will be in between 0 to 1, and reflectivity of surfaces depend upon direction of incident radiation as well as direction of reflection. Okay, so this should be kept in mind ki, this value of reflectivity is depend on the direction of incident radiation. Okay, now next definition is transmissivity. Transmissivity is denoted by tau. So it is defined as the fraction of total incident radiations transmitted across the surface. It is denoted by tau. Okay, so when radiations fall on the surface, so few radiations can be transmitted through that surface. For example, if we are having glass surface, in that case what will happen is radiations will be transmitted through the glass, and those transmitted radiations divided by total incident radiations are known as transmissivity. Okay, again the value of transmissivity will be in between 0 to 1. So one should know that ki addition of all these three things, that is absorptivity, reflectivity and transmissivity. So addition of these three things should be equal to 1. Okay, next definition is black surface. So black surface is the surface which absorbs all incident radiations on it regardless of its wavelength or direction. Okay, so we have discussed that whenever radiations fall on any surface, in that case three things are possible. Radiations can be transmitted through the surface, radiations can be reflected from the surface, or radiations can be absorbed by the surface. So black body is the body in which no radiations are reflected and no radiations are transmitted through the surface. All the radiations which are falling on the surface will be absorbed by the body. Okay, and that's why for black body value of alpha will be is equal to 1, because if 100 watt per meter square radiations are falling on the surface, then total 100 watt per meter square radiations will be absorbed by this surface. Okay, so value of this tau and rho will be is equal to 0. For given temperature and wavelength, black body emits maximum amount of energy. Okay, so it should be kept in mind that each and every body emits thermal radiation at its temperature. Okay, so if you compare any normal body with a black body, then black body will emit more emission as compared to normal body. For example, if we are having two bodies, one body is normal body and second body is black body, and both the bodies are at temperature 35 degrees Celsius. in that case what will happen ki black body will emit maximum radiation as compared to normal body. Okay, next definition is emissive power. Emissive power is denoted by small e. Okay, the radiant energy emitted per unit area, that is radiant flux per unit time from the surface at a certain temperature, is known as emissive power. Okay, so we have discussed one definition, that was radiosity. So radiosity was the total energy leaving from the surface, is known as radiosity. But here we are talking about only emitted radiation. In case of radiosity, along with that emitted radiations, we are also considering reflections or transmission. Okay, because that is also part of energy which is leaving the surface. But here in this emissive power, we are considering only the radiations which are emitted by the surface. Okay. Okay, so radiant energy emitted per unit area per unit time from the surface at a certain temperature is known as emissive power, and unit of this emissive power is watt per meter square. Okay, for example, if some radiations are falling on a surface, so that will increase the temperature of surface, and at that particular temperature the surface will emit some radiations, and those emitted radiations are known as emissive power of that surface. Okay, now emissive power of black body. So we have to understand what is the meaning of emissive power. So similarly, if the radiations are falling on some black body, and if that body is emitting radiation, then the radiations emitted by that surface is known as black body emission or emissive power of a black body. Now next and most important definition is for emissivity. Emissivity is denoted by epsilon. Okay, the emissivity of a surface represents the ratio of radiation emitted by a surface at given temperature to the radiation emitted by the black body at the same temperature. Okay, for example, we have seen what is the meaning of E. E is emissive power of a body and EB is emissive power of a black body. Okay, so if we take ratio of emissive power of any body to the emissive power of a black body at same temperature, then this ratio is known as emissivity of that surface. Okay, so if we try to find emissivity of black surface, in that case what will happen is emissivity of black surface divided by emissivity of black surface will get cancelled, and value of this emissivity will be is equal to 1 for black surface. Okay, so the value of emissivity should be always in between 0 to 1. Okay, so now we will discuss Stefan Boltzmann law. Stefan Boltzmann law is the most important law in radiation. It governs the radiation heat transfer. According to Stefan Boltzmann law, emissive power of a black body is directly proportional to the fourth power of absolute temperature of the surface. So for example, if any surface or if any black surface is having 1000 Kelvin temperature, in that case emissive power of that black body will be directly proportional to the fourth power of 1000 Kelvin. Okay, so if we write this same law for a normal surface, in that case this emissive power is directly proportional to epsilon into temperature to the power 4, because just now we have seen definition of this emissivity. Emissivity was equal to emissive power of a surface divided by emissive power of a black surface. Okay, where EB is emissive power of black surface, E is emissive power, T is absolute temperature of body in Kelvin. So we have discussed Stefan Boltzmann law. E is directly proportional to epsilon into temperature to the power of surface. This same law can be written by Q is directly proportional to AS into Ts to the power 4 minus T infinity to the power 4, where Ts is surface temperature, T infinity is surrounding temperature, AS is surface area, and Q is rate of heat transfer by radiation. Okay, if we remove this proportionality sign, we need to add one constant in this equation, and this constant sigma is known as Stefan Boltzmann constant. Okay, and unit for this Stefan Boltzmann constant is watt per meter square Kelvin to the power 4. Value of this Stefan Boltzmann constant is fixed, and this is 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. Okay, so if you are having any doubt, you can mention in comment section. Thank you.